Very good day to Madam Nor Azia. We are from Group A for Calculus 2, Tiohani with the number matrix of 270480.
And my name is Zong Jiaqing with the matrix number 270878.
And I'm Dan Sing Ying with matrix number 271572.
My name is Tia Ching Ni, matrix number 272170.
I am Neo Jia Jie. My matrix number is 269586.
Today we would like to present our group project, which is topic of application of integration in human circulatory system. So what is calculus? Okay. Calculus is the branch of mathematical which is study of rate of change that developed by two mathematicians, which is Gottfried Wilhelm Leibniz and Isaac Newton in 17th century. Furthermore, calculus can apply in many fields such as chemistry, physics, healthcare, and so on. But we are going to discuss about biology, which is human circulatory system. Circulatory system is developed by heart and vascular, which is also known as cardiovascular system, that consists of blood vessels that carry blood from and to the heart, that supply oxygen, nutrients, hormone, and remove waste products such as carbon dioxide, CO2. In all of these, we have decided two examples, which is blood flow and cardiac output. Next, I will pass to my members to continue and elaborate it.
Blood flow is the movement of blood in human body through the vessel. It's calculated by using the Poiseuille's law. The Poiseuille's law is derived by the speed of blood flow cross-sectional area of the blood vessel. For the speed of blood flow, the equation is delta V divided by 4 eta L. Delta P is the difference pressure between left and right end of the blood vessel. Then to calculate the cross-sectional area of the blood vessel is divided into 8 some interval. Then the delta Kr is very small, so we can approximate to a very thin rectangle. So we can just use the area of the rectangle formula to calculate the cross-sectional area blood flow. After that, we can find the total volume of blood flow through the entire cross-sectional area of blood vessel. To find the total volume of the blood flow, we need to combine the speed of the blood flow and cross-sectional area of blood vessel. Because of the blood vessel had divided into n subintervals, so we need to sum up all the subintervals by using the infinite series technique. As n is approaches to infinity, we can say that the range is between 0 and r. So we can get the Poiseuille's law, which is delta P 5 times r power 4 divided by 8 eta L. Now I will pass it to my next member to explain the example.
Okay, now let me to explain with the example 1. Assume a patient with high blood pressure discovered that the blood vessels are 20% closed by blood. How much more of pressure was needed to be injected by the heart to pump the same amount of blood compared to unclosed vessels? Now we let the F1 equal to blood flow for closed vessels and the F2 equal to blood flow for unclosed vessels. Since the same amount of blood are pumped into the blood vessels, S1 is equal to S2. And we had applied the Poiseuille's law that I mentioned just now. We assume the delta and L to be constant. We can get the P1 R1 power 4 is equal to P2 R2 power 4. Since the blood vessels are 20% closed, R1 is equal to 0.8 R2. And we apply it into the formula just now. P1 divided by P2 is equal to R2 power 4 divided by 0.8 R2 power 4. And we can get the answer P1 divided by P2 is equal to 2.4414. In the conclusion, from the calculation of previous slide, we can conclude that the blood pressure of the patient has been raised by 2.4414 times greater compared to unclosed vessels than the original pressure. Thank you.
Then I will explain about the cardiac output. Cardiac output is the volume of blood pumped by the heart per unit time. We measure the cardiac output by using dye dilution method, which is F equals to A divided by the integral of concentration of dye over time t in the interval of 0 to t. So what is dye dilution method? Dye dilution method is a process in which an amount of dye will be injected into vena cava and a monitoring probe will be inserted into the aorta. After that, the probe will measure the concentration of dye in the blood until the dye has completely cleared. So to derive cardiac output is equals to amount of dye divided by concentration of dye over time t. To derive cardiac output, we need to find the amount of blood pumped at some interval time t, which is F delta t equals to F times delta t. Next, we need to find the amount of dye at K sub-interval time, which is equals to concentration of dye at K sub-interval time times amount of blood pumped at sub-interval time t. Then the total amount of dye is equal to F times the series of concentration of dye at K sub-interval time with interval of K equals to 1 to infinity, which is equal to F times the integral of concentration of dye over time t at 0 until t. Then we will get the formula of cardiac output, which is F equals to A divided by integral of concentration of dye at the interval 0 to t, where t equals to total time, A equals to total amount of dye, and Ct equals to concentration of dye.
Now we will discuss about a question which is related to the cardiac output. The cardiac output of normal adult is about 5 liters per minute. A medical researcher carried out dilution tests on a volunteer that stayed at rest for 5 minutes. Then the volunteer will run for 100 meters and do the test again. For both the tests, 4 mg of dye are used and the time taken is 23 seconds. The concentration of dye for the first test is expressed as C1 of T, while the second is represented by C2 of T as the following. Since now we have the equation of the concentration of dye, we will then proceed to the integral of C1 of T. The limit of the integral are 0 to 23, which is the time taken of the dilution test. In this case, we will do the integration by using substitution method. We let u equal to t cubed, then du will be 3t squared dt, so that we can replace the t squared dt in the calculation by 1 over 3 du. Here, we also change the upper boundary of the integral. Since we have t equal to 23, then we will get u to be 23 cubed, which is equal to 12,167. Then we will proceed with the calculation. We will have the answer to be 45.8306. Now we are able to calculate the cardiac output after staying at rest, which can be calculated by dividing the amount of dye, which is 4 mg, with the integral of C1 of T in the previous section. We divide 4 with 45.8306 and we will have the cardiac output of 0.0873 liters per second. By changing the unit of time, we will get the cardiac output of staying at rest to be 5.2367 liters per minute. Next, we will find the integral of C2 of T. Just like what we have done for C1 of T, we integrate the equation from 0 to 23 by using similar substitution method, which is letting u equal to t cubed. Replacing t squared dt by 1 over 3 du and change the upper limit to 12,163. In this case, we will get the answer 33.3332. For the cardiac output after running for 100 meter, we divide the same amount of dye, which is 4 mg by the answer in the previous slide, 33.3332. Then we will get the cardiac output to be 0.12 liter per second, which is also 7.2 liter per minute. In this experiment, we have calculated the cardiac output after staying at rest is 5.2367 liter per minute, while after running is 7.2 liter per minute. The dye dilution test showed that the cardiac output of a normal adult after doing exercise will be higher than staying at rest.
So in the conclusion, in this our project, we had discussed and shown that calculus can be used in the field of biology to solve the problem in our daily life. So calculus is important in our real life, as it can be applied in many applications from different areas. So that's all for our presentation. Thank you.